Welcome, students, to the first one of my flipped videos, if you will. Again, don't expect one of these every night, but every once in a while, expect a little lesson at home, take some good notes, and we will go through this together. So I'm calling this 6.3 parentheses 1. This is going to be the first lesson from the textbooks 6.3, and we're actually going to get through a good amount today. But for this lesson, I'm more worried and more concerned that you guys understand the conditions and the definitions and a little bit what's going on. We will finish with a calculation, but I'm just saying hypothetically, if I were to quiz you on something tomorrow, it's going to be mostly on these definitions, not necessarily quizzing anything. I'm sorry, calculating anything. Okay, so confidence intervals for P, and I wanted to recall what P meant, or really define P. P we're going to call the population proportion, and that means it's the true proportion of the total number of favorable outcomes out of the total population. And a couple things about P is it's a parameter. It is the actual value of P would represent the true overall proportion of, let's say, high school students who like mayonnaise with their French fries. I'm pretty sure that proportion is like 0.99. That is 99%, right? Oh man, I just grossed you out. Just try it, okay? Don't knock it until you try it. So as you see here on the screen here, and I'm sorry this is so much information all at once, but you're always welcome to pause the video, that if I write P is going to be capital X over capital N. And capital X being the total number of total successes out of the N, the total population size. So for instance, maybe there's 1,200 JSerra students, and maybe only 300 of them actually liked to eat mayonnaise with their French fries, then P would be 300 over 1,200, or 3/12, or what is that, 1/4, right? 1/4, or 0.25. Now a couple things about P. P can be known, and usually in small populations. I guess we could, if we could take a census of the school, we could survey all 1,200 students and find out exactly how many like mayonnaise with their French fries. But typically it's unknown, and it can also represent a probability, maybe like a basketball free throw shot. In that case, P is not only the proportion of successes over the total number, it's kind of the probability of success too. Moving on to the next slide. Okay, let's try some examples here. Calculate, if possible, and define P. So not only tell me what the number P is, but tell me what that means. So A, 128 students in a school of 1,200 ride the bus to school. Part B, 1.87% of widgets are defective. And Part C, 487 from a simple random sample of 1,000 voters favor candidate A. So if you can try this, you can pause the video and see if you could calculate and define P if possible. Parentheses, if possible, might mean there might be some situations where it's impossible, right? Right. Okay, so Part A. Yeah, in this case, P, so again, P is supposed to represent the proportion of the whole population. So in Part A, what's the population? Well, it's in a school. So we are representing, this would be represent the whole population of 1,200 students at the school. So P would be 128 over 1,200, which if you put that in your calculator is 0.1067. It's 10.67%. And I'm defining P here next to it, where P is the proportion of students at this school who take the bus to school. Okay, how about Part B? Is that a parameter or is it a statistic? 1.87% of widgets are defective. Well, it should be a parameter, right? So good. Yeah, in this case, P is 0 0.0187. Watch that 0 right there. Where P is the proportion of all widgets that are defective. Okay, how about number C? Can you find the population proportion here? 487 from a simple random sample of 1,000 voters favored candidate A. What? You said you can't figure it out? Why can't you figure out that this is why can't you figure out what P is in this case? Good. Well, this came from a sample now, didn't it? This is not all voters. This is merely a subset, 1,000 voters of all voters. At least it's a random set. A random sample, that is. So, yeah, in this case, we don't know what P is since this is a sample, but P is the unknown proportion of voters who favored candidate A. So what are we going to be doing here? Well, in this chapter, in this section, we're going to be trying to estimate what P is. For instance, in part C, what is the true proportion of voters who favored candidate A? And do you think he'll win? Do you think he'll get more than 50%? Or could we rule it out? Is there no way he's going to get over 50%? We're going to answer those questions. So P's counterpart is P hat. Watch the hats here. So P hat, we put that little caret over P. P hat now represents the proportion of favorable outcomes in a sample of size little n. So in our last example, for example, we didn't have the true population proportion, but we had the sample proportion. We had a proportion of a sample of 1,000 voters. So in general, P hat is going to equal x over little n, and little x just being the number of favorable outcomes, that's from the sample, and little n is the sample size. So the candidate A example, can you figure out what P hat is in this case, since we know we don't have the true proportion of all voters, we have a sample? Oh, you're already done? Good job. P hat in this case is 487, that was our, the number of voters who favor candidate A, over 1,000, so 0.487, which, yeah, literally is 48.7%. But we're going to be writing these not as percents, just as decimals, some number between 0 and 1. If your proportion's ever negative, you did something wrong, minus points, and if it's positive, if it's over 1, that is, you also did something wrong, minus points. Don't leave your answer as the proportion is 1.1. You pretty much get double dinged for writing something like 1.1 because it's not a valid proportion. Alright, I didn't want to spend a ton of time on this because it does get kind of confusing. But we say that P hat is an unbiased estimator of P. What that means is as long as your samples are random, as long as you're taking simple random samples, that P hat should be a pretty good estimate of P. And when we say unbiased, what we're kind of saying is, like, if everybody did it over and over and over, the average of everybody's sample proportions should be about the real proportion P. Or another way of saying it too is that it doesn't tend to overestimate any more than it underestimates the true proportion. So again, the goal is to use our sample data, our sample proportion, to estimate the true proportion from the whole population. Yeah, don't worry about that one. Okay, so let's just get into the nitty-gritty here. Let's actually look at constructing a confidence interval for P. I made a few mistakes here. There we go. Okay, so our confidence interval, sorry, I have a little mistake here I got to fix. Our confidence interval for P, and again by P I'm talking about the parameter P. P hat is the statistic, comes from the sample. So it's going to be our estimate, which is P hat, plus or minus our margin of error. And the conditions, the sample has to be random. Again, if the sample's not random, it's in no way going to be a good representation of the entire population. And the normal conditions, we have to check these. And maybe I'll spend a little bit more time on the normal conditions, but this pretty much stems from our last section 5.5 when we talked about using a normal approximation to a binomial event. And it's the same conditions, NP and NQ have to be greater than 5, although I'm going to put a little asterisk on here. Since we actually don't know what actual P and actual Q is, we're going to have to put little hats over that. That is, it's the number, it's N times P hat has to be greater than 5, or N times Q hat has to be greater than 5. Hang on, that first hat was just awful. Wait, we need that again. Hat, wrong place, sorry, it's my first day. Never done this before, it's my first day. I'm learning. Okay, then our level C percent confidence interval is going to be P hat. That's our sample proportion, plus or minus our critical value of Z that we saw in 6.1 times the square root of P hat, Q hat divided by N, and where Q hat is going to be 1 minus P hat. That is, it's the number of failures. The proportion of failures, I should say. Excuse me, it's my first day. Okay, fine, it's my second day. So let's see if we can piece this all together. So our candidate A example, again, we had a simple random sample of 1,000 people, 487 of them would support candidate A. So let's construct a 95% confidence interval for the true proportion of voters who support candidate A. We can do it. You excited? A little sad? Okay. All right, a couple of things we want to do. First thing, it doesn't hurt to find out what our sample proportion is, our P hat, to start out with. So in this case, it was 487 divided by a nice 1,000, came out to 0.487. How about the conditions? Are our conditions satisfied? Well, was it random? Yeah, the problem said it was a simple random sample, so that's good. We needed that. Where is it? That button. Random check. So this is going to be what I'm calling the normal condition. And again, why am I calling it the normal condition? Because what I'm doing is I'm making sure my sample size is large enough so that I can use a normal approximation to the binomial curve like we did in section 5.5. So I'm going to have to check our NP hat greater than 5, and is NQ hat greater than 5? Something works out pretty nicely with these. For example, again, our N was 1,000, that's right there, and our X in this case, or our number of successes, is 487. So N is 1,000. P hat, I'm just going to use the fraction that I started with, is 487 over 1,000. Is that greater than 5? Well, check it. These denominators just cancel. That was 1,000, excuse me. And I'm left with 487. And what was that number of 487? That was the number of people who supported candidate A, or in this case, it's the number of successes. So for Q hat, I could either do 1 minus 0.487. Yeah, may as well. That's going to be Q hat, so that's going to equal 0.513 if my math is right today. So if I did N, which was 1,000, times Q hat, which was 513, excuse me, is that greater than 5? Well, that's 513. Last time I checked, that's certainly greater than 5, much greater than 5. That's great. And if you actually look at this number, what this number represents is the number of failures, or in this case, the number of people who didn't vote for candidate A. And in fact, I could take these two numbers and add them together, and they'll add up to my sample size. Almost there, folks. Okay, so now our conditions are satisfied, so let us calculate our confidence interval. And we'll need a calculator for this. So our p hat was our sample proportion. We already got that. That was 0.487. Notice all these numbers are going to be decimals between 0 and 1. Plus or minus z star for a 95% confidence interval. You can get this off the t-table, 1.96. And now times p hat, which was 0.487. There's a decimal in there somewhere. Yeah, there, that's a decimal place. Times q hat is that, all divided by 1,000. And after crunching those numbers, the right-hand side, the margin of error on my calculator, excuse me, after some rounding, I got 0.487 plus or minus 0.031. Now just think about what this means for just a second, because this is what you see on the news, right? 48.7 plus or minus 3.1%. That's exactly what that is. How many times have you seen that on the news, right? Candidate A is in the polls with 48.7% of the votes, plus or minus 3.1%. Well, if they used good statistics, and hopefully they cited their research, you could see how they actually took their samples, and this should be the methods, the methodology that they used exactly. So on the low side, that is going to be 0.456, and on the high side, so again I'm adding my margin of error, so that's 0.518. So we are 95% confident that the true proportion of voters who support candidate A is between 0.456 and 0.158, or between 45.6 and 51.8. So just I'm just going to leave you off with this question here, and maybe you want to pause the video and just think about it. Let's just make it easy and say that candidate A needs over 50% of the vote to win the election. Do you think that this particular poll that you took is not going to give you enough information to determine, beyond a really good reasonable doubt, that your best friend candidate A is going to win the election? And the answer to that is we don't know. We don't know because we're saying that could be anywhere between 45.6%, in which case he or she would lose, and it could be as high as 51.8%, in which case he or she would win. So unfortunately, you've got a margin of error of 3% here that you just can't determine whether candidate A is going to win the election with this particular poll. So what could you do? You can retake the poll and increase the sample size. Okay, so this is your first video, and you're going to get quizzed on some basic definitions and some pretty easy concepts. You don't have to do the last part, calculating the whole margin of error, the whole confidence interval yet, even though we'll do that in class. You're definitely going to want to know your definitions and some of the general concepts and like those conditions for your quiz. Thank you.